Nonces are difficult for even computers to figure out, and the competition between miners to solve nonces with more high-powered and power-thirsty computers translates into real costs. You'll recall that miners on a blockchain are nodes that produce blocks by solving proof-of-work problems. If a miner produces a block that is approved by the electronic consensus of nodes, the miner is rewarded with a specific number of coins, called a block reward. At present, the node that solves the block hash is awarded 6.25 BTC, but this figure is adjusted lower over time as we approach the limit of 21 million Bitcoin that is built into the principles of Bitcoin. This block reward is not the only incentive for miners to keep running their hardware, however. They can also receive transaction fees that users pay to send transactions. Transaction fees can vary depending on the number of transactions being sent on the entire network at any given time. More network traffic can mean higher fees. Even though fee amounts can be chosen by the sender in most cases, miners will always prioritize transfers with higher transaction fees. Therefore, unless you're willing to pay a rather hefty fee, your transaction might take a long time to be processed if network traffic is bloated. In Bitcoin, the difficulty of mining the correct nonce to solve the hash increases with more processing power. Based on the rules of Bitcoin, in order to keep the amount of time needed to mine one block at approximately 10 minutes, mining difficulty is recalculated every 2016 blocks by the program that governs Bitcoin. Miners have moved from being able to mine using an old spare laptop to GPU rigs to huge farms with hundreds of specialized application-specific integrated circuits called ASIC or ASIC machines, and these machines consume massive amounts of electricity. And this has led many detractors of proof-of-work cryptocurrencies to claim that mining is an environmental disaster. Speaking of the Bitcoin program, all blockchain consists of individual behavior specifications, a large set of rules that are programmed into it. These specifications are called protocols. The implementation of specific protocols essentially made blockchain what it is, a distributed peer-to-peer and unsecured information database. The blockchain protocols ensure that the network runs the way it was intended to by its creators, even though it's completely autonomous and isn't controlled by anyone. When we talk about Bitcoin, the Bitcoin blockchain has the following principles that are set forth by the Bitcoin Foundation. There'll be a maximum of 21 million coins. There should be no censorship, meaning that nobody should be able to prevent valid transactions from being confirmed. It's open source, which means that the source code behind Bitcoin should always be open for anyone to read, modify, copy, and share. It's also permissionless. There's no gatekeepers that would ever prevent anyone from being part of the network, either as a user, a node, or a miner. The system is pseudonymous. There's no ID that should be required to own or to use Bitcoin. Bitcoin itself is also fungible, meaning all coins are equal and should be equally spendable. And transactions are irreversible, meaning that once blocks are confirmed and set in stone, blockchain history should be immutable. A foundation, which is the most common for permissionless blockchain, also decides on the rules. For Bitcoin, for example, any changes to the principles above require 100% approval by all holders of BTC. Given that the industry estimates are around 20% of outstanding BTC being lost forever or stranded in wallets, changes that require 100% approval will be nearly impossible. Some of you may be wondering, with respect to permissionless blockchains, what about software updates? How can we get consensus among a distributed network of nodes to change the underlying software or code without any interference from a central authority? As we talked about earlier, for contentious software updates, particularly where there's value of the users involved, consensus can be hard to achieve. In instances where full consensus is not achieved, the network will be forked. These forks can arise when a change in the software is not compatible with an earlier version of the code, and some users of the network may wish to remain on that old version of the code. Various networks, including Bitcoin and Ethereum, have experienced hard forks as a result of a lack of consensus for contentious software updates. A hard fork essentially creates an entirely new currency as it's a permanent divergence from the previous version of the blockchain. One path will follow the new upgraded blockchain, and the other one follows the old path. The users mining that particular blockchain can elect to upgrade and follow one path, or not upgrade and stay with the other. This is called backwards incompatible. Bitcoin itself has experienced a few hard forks, with offshoots being named Bitcoin Cash, Bitcoin XT, Bitcoin Gold, and Bitcoin Classic. However, all of these hard forks have met with limited success, while the original Bitcoin has thrived. There are also soft forks in blockchain technology, where a change is made to the software protocol that doesn't clash with the code, meaning that upgraded nodes can still communicate with the non-upgraded nodes. Soft forks are backwards compatible, and after the soft fork, still only one blockchain exists, as both upgraded and non-upgraded nodes work on the same chain. Old nodes could still validate blocks and transactions, but they just wouldn't understand them. Some fields are only readable when nodes switch to the newer software, which allows them to get additional data. When structured properly, blockchain records can be confidential, hard to forge, amend, or even tamper with. Blockchains may be fully public, such as Bitcoin, so that anyone can verify and potentially append to the chain. These are called permissionless blockchains. Or they may take the form of a private blockchain, so that only permission users have access to the chain, say like our Amazon shipping tracker, which can only be updated by Amazon. It's somewhat similar to the concept of an intranet, which is permissionless, versus a corporate intranet, which is permissioned. And in terms of economic advantages, blockchain technology reduces verification costs to validate and process a transaction, as well as privacy or security and networking costs, which economists call economic rents. Decentralization also has the advantage of not having a single point of failure, and we can avoid censorship. One other consideration that's a benefit of blockchains, especially when it comes to moving value digitally, is that users are not at the mercy of market trading hours or banking hours, as there is no central authority or agency that intermediates the transfer. So blockchain transactions can be truly 24/7. There are, however, drawbacks and limitations to blockchains and the crypto technology behind them. For permissionless blockchains, they are harder to coordinate, govern, and scale, since no one centrally manages that ledger. This makes things such as software upgrades or required amendments to fix security holes more difficult for decentralized, permissionless ledgers. By design, blockchain technology requires each node to work independently and compare the results of their work with the rest of the network. So reaching a consensus can be very time-consuming. Because of these capacity and latency issues, blockchain networks are very slow compared to traditional transaction technology. For example, Bitcoin's throughput is between 7 and 10 transactions per second, while Ethereum, another well-known cryptocurrency, is approximately 20 transactions per second. In stark contrast, the centralized Visa network can process 65,000 transactions per second, according to their website. The size of the blockchain grows as transactions are appended onto the chain. So, for example, as of July 2021, the blockchain for Bitcoin is almost 350 gigabytes in size and growing. Now, blockchain transactions also provide probabilistic finality only after multiple blocks have been added to the blockchain. The finality of a transaction increases as that particular transaction moves deeper into the blockchain, making it less likely to be reversed, and the probabilistic finality of blockchain transactions increases based on the length of time for block formation and the number of blocks subsequently added to a chain. On average, Bitcoin blocks are formed every 10 minutes automatically, and each block contains more than 500 transactions. Given the recommended 6 blocks to be added before a transaction is considered probabilistically final for Bitcoin, it would take around 60 minutes at the present. Consensus protocols can also be subject to what's known as 51% attacks, whereby a majority of users try to reorganize the blockchain, effectively rewrite the ledger, double spend, or censor transactions. One other limitation is that blockchains are not always related. For example, Bitcoin and Ethereum chains are not compatible, which presents interoperability issues when you consider that at the beginning of 2021, there were over 4,000 different cryptocurrencies and multiples of that in non-currency blockchains, few of which speak to each other. Lastly is the concept of privacy. As I mentioned earlier, there are closed, permissioned blockchains that are very secure and private, but for a permissionless blockchain, a common misconception is that it is completely anonymous. However, in actuality, blockchain and most cryptocurrencies are pseudonymous. While the person or organization behind a Bitcoin account, called a digital wallet, may be unknown, the address is publicly known. It was based on this that the FBI was recently able to recover most of the Bitcoin ransom that American pipeline company Colonial paid to a hacker organization called DarkSide.